My name is Veena Misra. I'm directing the National Science Foundation Center, Nanosystem Center called ASSIST. I won't repeat the acronym. And I'm also a professor of electrical and computer engineering at NC State. This center is a partnership between 5 different universities, actually 4 partners and 2 affiliate universities, which are listed down here. And I will refer to some of the work that has been that's being done in these universities as I go through my presentation. The outline of my talk is as follows. I'll first talk about what health and environmental sensors enable as we go towards a correlated, interconnected world. What are the critical sensing modalities that we need to address? And what are some of the key barriers facing sensor proliferation as we go into the future? These include sensing modalities, form factor, low power operation, data analysis, and storage. And then I'll summarize. And I'm going to give you about a 30-minute overview on sensors and health and well-being, and then I'll turn it over to my colleague, John Muth, who's going to give you some more detailed perspective on energy considerations of these sensor systems. So the National Academy of Engineering has put forth many grand challenges that face our global future, and one of them is the area of advanced health informatics, and especially as it relates to the staggering cost of healthcare. Just in the US alone, in 2010, the healthcare costs exceeded about $2.5 trillion. Now, what's scary is that majority of these healthcare costs are associated with chronic diseases. For example, heart disease, diabetes, asthma, cancers. These are all categorized under chronic diseases. And these diseases are lifestyle diseases and require perhaps a lot of management costs associated with improving the outcomes. As an example of how big this condition is, heart disease is the leading killer in the US and globally, and we have over 300 million asthmatics that are suffering from respiratory diseases. Now, chronic diseases are triggered by many factors. They include genetics, lifestyle, environment, and stress. And while we may not be able to do much about your genetics, we can certainly give you tools to monitor and improve your lifestyle choices, monitor and improve your environmental exposures, and reduce your stress. This plot is taken from Christensen, and this basically shows all the risky actions that a user can intentionally or unintentionally take. For example, not having good nutrition, excess alcohol, smoking, poor diet, little or no exercise, and how these risk choices lead to risk factors, such as excess body fat, high blood pressure, and so forth, and how these risk factors, as they add up, will lead to chronic disease development. And these chronic diseases will then lower the quality of your life and increase the healthcare costs. So sensors, if they're designed correctly with low power operation, comfortable, wearable, wireless, with intelligent information coming out, can significantly impact the outcomes of chronic diseases. So here's a plot from IBM Global which shows the population of the world in sort of 3 different groupings. On the far left are motivated, healthy people, and I'm sure many of you are in that category here. These are folks that monitor their fitness, they make good choices, they use technologies to help their outcomes of their at life, and these individuals actually incur very low healthcare costs. On the extreme right are chronically monitored people. These, unfortunately, are folks that are suffering from multiple chronic diseases, and their healthcare costs are relatively high. But the opportunity that we face with sensor technologies in the future is really the space in the middle, where we have a large percentage of the population that is vulnerable, that is seeking to improve their quality of life. They maybe have one chronic disease condition that's beginning to come around, or maybe they have several. But these are the people that if we empower them with sensor systems that are intelligent, low power, wearable, wireless, we can really have an impact in the global health of chronic diseases. Now I want to give you another reason why sensor systems can really empower the future health outcomes, and that's the role of environment. So we are exposed in our daily routines to different types of environments as we go in and out of buildings, as we drive in our cars, as we go in and out of industry buildings. And it has been known for many, many decades that there is a strong correlation between environment and health. For example, if you take the case of asthma, about 8.5% of the population in the US suffers from asthma. And it's well known that environmental agents exacerbate asthma outcomes. In fact, ozone is associated with developing asthma. And so monitoring a person's individual environmental exposure can allow us to treat the asthmatic patient more effectively and rapidly. Another example is cardiovascular disease. It's also known that particulate matter, for examples, is on the highways or in diesels or in wood stove in kitchens in countries, that can generate enough of an impact on cardiovascular patients to increase mortality. And these two figures on the right are from David Peden, which show that the percentage risk of myocardial infarction increases as you have ozone exposure or particulate matter exposure. So these are real conditions that impact chronic disease outcomes, and being able to monitor somebody's personal environmental exposure is critical. So as a specific example, here's a schoolgirl who suffers from asthma. She's exposed to different environments, for example, her school, her highways, her house isn't near a highway. She visits relatives who may smoke. The point being that her exposure to environmental toxins changes as she moves around in her daily routine. And so we need to understand exactly how to monitor somebody's personal environment. So what we are going for are sensor systems that are non-obtrusive and that can provide data both on the health parameters of the individual, but also their personal environmental exposures. So as an example of what we're talking about, on the left table are some critical environmental pollutants, and on the right are some corresponding health responses associated with them. So for example, if you monitor ozone on somebody's personal environment, at the same time you can also monitor their lung sounds, which will give you a correlation between ozone exposure and the respiratory response. Another example will be monitoring somebody's particulate matter exposure. PM 2.5 is particle sizes 2.5 microns that are known to cause the largest impact. And also at the same time you monitor their heart rate. So now you can get the correlation there. So the idea being that you want to be able to correlate health and environment. And that's a real opportunity as we go forward. In the area of health, it's important not just to monitor motion and activity, which is very, very popular at this time, but you also want to monitor other important things in the body, which can give you a good idea of what's actually going on. These include not only heart rate, but interstitial fluids, biochemical agents in interstitial fluids, for example, cortisol or lactates, and these give you a measure of the stress level, a real physical stress response of the individual, oxygen levels as well. And by having multiple streams of sensor data, you can now start putting those together and getting a better understanding of what somebody's health status is. So that's sort of the background motivation of what sensors can do for us in area of health and environment. For a sensor system to be successfully used and adopted, it has to have some essential components. And so here is an example of what a sensor system could be used, in what forms it could be used as, whether it's on a chest patch for an EKG node, or whether it's on the arm as a blood pressure node, or in other parts of the body for other sensing modalities. The basic feature of these sensing platforms is that they should be wireless and they should be wearable. They should be comfortable. The data coming out of it should be very reliable. That's one of the biggest features we have to go for, is reliability of data. Otherwise, the sensors will be not validated. And a key feature is, and you'll hear more about this in the next talk, is they have to have ultra-long battery lifetime to really enable long-term monitoring and to improve the adoption and compliance by the user. So here is a schematic of what a typical sensor platform will look like for environmental and health sensing. It has key features. For example, it has sensors down here. For example, gas sensors such as ozone or NO2. It has health sensors. All of these inputs from the sensors feeds into the system on chip, which is typically based out of CMOS technologies. This SoC has tremendous opportunity for power optimization. You can also have energy storage in the form of either battery or supercapacitors. This system has to be wireless, so it will be connected to an antenna system. And it has to also, at the same time, have features of biocompatibility and enhanced functionality by being modular. The data that's processed in this SoC then goes to a data aggregator, where information is converted from just simple data to intelligent decision-making information, and that requires tremendous amounts of signal processing. So that's sort of the schematic, a very rough schematic of what a sensor platform will look like. There are some key technologies that are important to enable the successful operation of this. And these include energy harvesting and storage, which I'll talk about a little bit, health and environmental sensors, ultra-low power system on chip, and packaging and reliability. So let me give you a brief overview on these technologies. So what are the desired sensing modalities that we want to cover for health and environment? So here is a picture of here's a picture of the human body, and it shows the various locations where strain can occur and how strain can be measured using physical or inertial sensors such as accelerometers and so forth. And these strain points can give you a lot of information about the body's health. Here's another schematic from Body Media showing the various locations on the human body where different types of modalities can be obtained. These include skin temperature and heat flux in these regions, galvanic skin response in these purple spots, and acceleration in many, many more areas. And the idea is that we have lots of places on the body that we can put sensor platforms on and obtain very useful information about the response. Now, what's perhaps more interesting in terms of medical outcomes is this table that was produced by Eric Topol, who you may have heard of. And this lists the various chronic diseases that the population is suffering from and what kinds of sensors we need to address those various chronic conditions. For example, in the area of asthma, we want respiratory rate and forced expiratory volume. In the area of depression, another area where sensors can have a huge impact, you want to make sure that the patient is compliant with the medication. In the area of heart failures, you want to measure the cardiac responses and blood pressure, and so on and so forth. So lots of opportunity for us, for the sensor world, to build technologies that can help these, provided we have the features that I mentioned a few slides ago with their low power, they're wearable, comfortable, wireless, and give intelligent data. So there are many, many sensors on the market today that have been used by many groups to obtain information about activity, about gait, about compliance, and they're sort of categorized into three different areas. Biophysical and inertial sensors, these contain mostly your accelerometers, your gyroscopes, your magnetometers is all in the category of biophysical inertial sensors. Then you have bioelectronic sensors. These include heart rate EKG sensors. They also include skin conductance, and even humidity sensors can fall in this category. And then you have the biochemical sensors. These are the more sophisticated sensors that give you a lot more information, but are still new in the maturity level. So I would say that in terms of commercially available, very, very good performance level, the first category is the most mature, and the opportunity to really make an impact in sensors for health and environment really lies in the biochemical area. So I would now like to show you some of the main modalities and the challenges associated with these modalities and how we can address them. And so I won't have time to go into every single one of them, but to give you an idea, in the area of electronic sensing, once you put electrodes on the skin, you can get a lot of information out, including all kinds of EXGs, also skin conductance, temperature, and humidity, and they can be related to a variety of conditions. But the biggest challenge in these types of sensors is the contact to the skin. The dry skin contacts are desirable. If you want long-term monitoring, you could build a system that is ultra-low power, but the contacts and the skin problems at the contacts will limit how long you can use that system. So new techniques in getting rid of the adhesive-based contact systems will be very influential in making electronic sensing pervasive and longitudinal. In the area of optical sensing, very, very important not only for oxygen levels in the blood, but also for glucose sensing. There are some studies that are showing very good results with optical sensing for glucose. But the biggest challenge here that we face is if you want any kind of decent lifetime of the device, you need to lower the power levels. And there's work going on in many groups, and I've just shown one here from Boskert's group, where they're looking at a systems approach to lowering the total power level of pulse oximetry systems. In the area of acoustic modalities, there are also many options here. One clear one for health impact is microphones. Microphones will allow you to measure different kinds of body sounds, which will give you a lot of information about somebody's respiratory response or somebody's blood flow. There are some opportunities here, relatively new field, in where we can understand the body better, but again, the power levels are an opportunity for us to bring them down. Biochemical areas, as I mentioned already, biochemical sensors are a huge opportunity for us. They can give us lots of information about the body. But again, the skin interface to the fluids that are being extracted is a key problem here. And continuous operation is also a challenge. Motion sensors are relatively mature. These are the ones that we have all over the place in our cell phones and in some of these fitness wearable devices coming out. And again, power levels can be improved, but in general, this is the most successful sensing modality so far. And environmental sensing, I hope I've convinced you that environmental sensing is a key new opportunity for us. But again, here, gas sensing of the environment, whether it's ozone or volatile organic compounds, all of these require sensor systems that are specific, that are sensitive enough to measure the levels that we need to be measuring and can run for long periods of time. So now let me talk about form factor. So I've sort of given you the types of modalities that we're interested in, and you'll hear about all of these during the conference. Sensors location. This is an important feature of where these can make the biggest impact. And so I would like to say that smartphones and cars are sort of old news. Sensors and smartphones have been around for a long time. Even just last year and 2 years ago, people have started adapting the cell phone cases to be able to give health sensing information. For example, the LiveCore product gives you EKG as in the back of the smartphone case. You have all kinds of activity monitoring that you can do with smartphones. In cars, many car companies, the example here is Ford, is equipping their cars with sensors that can allow you to measure environmental exposures outside and also allow you to have EKG electrodes on the car itself, which gives you information. So that's sort of a established opportunity, and companies are moving in this direction. The new opportunities are really in the case of home monitoring, where you have a variety of applications shown here. But then the one I really want to focus on here is on the body. This is where we can empower the user and empower the doctors to understand what's going on. And so in the area of wearable devices, there's a lot of products that have been coming out. Primarily in the fitness space, which unfortunately is also the space where the healthcare costs are the lowest. We really want to make sure that we have similar technologies for the chronic cases where the healthcare costs are really, really high. But this is going to be propelled by the explosion of devices in the fitness space. But there are lots of products coming out. The latest one is Fitbit Force. And these products really demonstrate that there is a need for these devices. There is a demand. And so it establishes the sort of the market space for these technologies. And as shown here by this Biointelligence study, the millions of devices shipped in 2017 is expected to be over 300. So clearly it's a great established platform, the wearable space. I also like to point out that there are some earbuds that are coming out as well that provide some information. But within these sets of devices, there are some clear opportunities. The battery lifetimes are not very long. Maybe a day. In some cases, if it's just one modality of sensing, it could be a couple of days. But that's an opportunity. The form factors. Right now, these are all fairly large. And in many cases, they are limited by the battery life. And so the battery size, I mean. So there's a huge opportunity to reduce the form factor of these devices. They are generally not open source or configurable, so there's an opportunity there as well. And increasing the number of available sensing modalities is an essential component of achieving the vision that we want in global health. I'd like to spend 1 minute on the Wristband platform. Some of you may have seen this in the news coming out that many companies are either having a prototype or even selling devices that are on the wristband. And this is really, so far, wearable electronics. But wearable electronics will soon become wearable sensors. And so by combining wearable electronics like Qualcomm's or Samsung's watch with sensors that can sense things on the body, we are now talking about a highly functional system that can do both. But the biggest problem with all of these devices is the battery life. And I won't read this quote, but really the battery life limits the operation and the usefulness of these systems. So let me spend a few minutes on giving you some issues regarding battery life. And as I mentioned, my colleague John Newt will be talking about this in significantly more detail. So a sensor system consists of, as I mentioned to you earlier, consists of many components. Stored energy and harvested energy are the sources of power, whereas the sensors, the communication block, the computation block, and even the energy management block are the components that consume that power. And we need to have a good balance between energy supply and energy consumed. And this balance is achieved by the way the sensor system is used. If you can reduce the frequency of sensing, you can significantly improve the battery lifetime, provided you don't lose information in the case where things are changing rapidly. So energy demands depend on a lot of different parameters here, but really this is the opportunity to design the components based on achieving this balance. So in terms of self-powered operation, where eventually there is no battery needed, there's a roadmap that we're going to have to follow. Today's devices run on some sort of rechargeable battery, coin cell or similar. And the advantage, of course, is it's low cost, it's reliable, but the disadvantage is that the form factor is limited in size. And the power densities and so forth are also not going to be very high for batteries, which prevents some sort of high power applications. In a few years, we expect that we will go away from the coin cell battery, that's the roadmap, and go to some small thin film or a printed battery that's supported by harvesters and perhaps supported by capacitors. This combination allows you to lower, to increase the power density, to improve to some degree the form factor, but eventually the goal is to go to completely battery-free technologies where we have harvesters feeding into supercapacitors. And the ultimate advantage here is form factors. And now instead of having wristbands and patches, we can insert sensors inside clothing, little slivers of sensors inside the watch or inside jewelry, and that's really enabled by going away from batteries. And one of the key enabling technologies that helps us to get there is nanotechnology. And the reason is nano allows you to lower the power consumption for all the components that need power. Nano will allow you to reduce the power consumption of electronic devices. Nano will improve the energy harvesting efficiencies in the area of thermoelectrics and piezoelectrics. These are obvious choices to use from the human body. And nano in the sensors area will allow you to increase the surface to volume ratio. Instead of a metal oxide film, you can go to a metal oxide nanowire, and this will allow you to lower the voltage needed and increase the sensitivity as well. So these combination of these three nano-enabled technologies can help us get to this ultimate roadmap of no batteries needed in these sensor systems. I'll give you a couple of examples about how these low power systems are actually successfully being demonstrated. This is work from Calhoun's group at UVA, which was, he designed a system on chip using a subthreshold CMOS technology. This is not a very aggressive node, it's 130 nanometer node. But the point is that with clever designs, the group built a 4-channel EKG system that ran at a power level of less than 30 microwatts. And this chip was run off a complete energy harvester. There was no battery included in this demonstration. It ran off a commercial thermoelectric device. And so this shows the power of really optimizing power consumption across the board of the sensor system. A huge area of power consumption is the radio, is the wireless capability. And even there are some opportunities that the radio engineers are working on. Right now, Bluetooth LE seems to be the major wireless communication platform for many of these wearable devices. But even Bluetooth LE is not really that low in power level. And to bring the power levels further down, we need to go to different frequencies. And here is an example of some of the ultra-wideband radios that have been developed at Michigan and David Wenslow's group, which show extremely low power consumption. Bluetooth LE would be magnitudes higher than the values here. Range is a little bit small. It's just a couple of meters, but we can give up range for power because most of these wearable devices are expected to communicate to a nearby base station like the smartphone. So the trade-off between power consumption and the range is a good trade-off to have. And accordingly, antennas have to be designed that work at these frequency ranges. I'd like to just give a plug-in for devices. This is another opportunity where extreme energy efficiency can be obtained. This is a plot shown by Intel with the energy per computation as a function of the delay time. And you really want to be in the lower left part of this plot. And so the lowest we can ever, and this is simulations, the lowest we can ever get so far is with a graphene nanoribbon TFET, a tunnel FET. Of course, we don't even know how to make a nano ribbon out of graphene, much less a TFET. So that's sort of a theoretical point. But really, the next best option is to go for a heterojunction tunnel FET or a 3-5 tunnel FET. And if you don't know what those are, I'll be happy to explain those to you later. But these are devices that work like a CMOS device, like a MOSFET, but under slightly different operation conditions, and gives you much, much better energy efficiency. So if you're in the device area, this is an opportunity to get ultimate energy efficiency. And finally, I'd like to now talk about storage and analysis. So all of these sensor systems all the modalities that I have mentioned, ranging from the EXG devices to visual recognition, stretchable fabrics, air quality sensors. I didn't talk about brain activity, but that's a huge opportunity, and so on and so forth. All of these devices are generating data. And there is going to be so much massive amounts of data that we have to have a big data strategy just to address and understand what this data means. And this is Internet of Things by Cisco, clearly showing that this is going to be a huge opportunity, but also a huge threat in order to make this field successful. And so an example here is the individual wearing a chest patch or a wristband. This chest patch and wristband is generating a lot of data. This data is then going to go to the smartphone. From the smartphone, it's going to go to the cloud. From the cloud, it may even go to the fog first. It depends on the application. There might be other sensor modalities picked up at the smartphone level that are not actually on the user node, such as GPS and so forth. And now what do you do with all this data? How do you analyze this data? And so here are some concerns on data trends. We're dealing with a lot of large amounts of data. We have to understand how these data can be fused with each other. How do we go from big data to personalized data? Another opportunity that's coming about is if you have a cohort of people where you know what their general data looks like, can you use that data as a proxy to understand somebody's individual data that you don't have? And so here are the needs and the barriers for addressing the data issue. I won't go into all of them, but really achieving processing of data and developing algorithms is clearly an opportunity for this community, and pattern recognition is another required feature. So I'd like to show you my second to last slide. I won't go into all the details here, but these are the core components of sensor systems. They range from the individual components, the individual materials, devices, and the fabrication techniques. Manufacturing comes into the picture here as well. We have energy harvesting and storage, low power electronics and communication, wearable platforms and sensing modalities, data acquisition and management, medical customers, these are important, and finally the user experience. And really, to make these things successful, we need to take care of many, many parameters, a few of them that I have been able to tell you about today. So my last summary then is personalized health and environmental monitoring can lead to significant insight into wellness management. As a country, we have been managing illness, and we need to transition to managing wellness. Long-term monitoring is a huge opportunity because it'll open up new paradigms in understanding disease progression. And we believe, and a lot of you will also believe, that long-term monitoring has to be enabled by self-powered systems, ultra-low power systems, where the battery lifetime can be very, very long. And sensor systems have other required components that should be met: form factors, reliability and power management, and of course the issue of data analysis. And so I've given you sort of a big picture perspective on what we want from our sensor systems, and I would like to stop now and see if anybody has any questions for me. Yes?
And can you comment on, you mentioned a lot of advantages regarding nano, and when you go to nano scale, things are probably less controllable when you attach things to body or software or inside the body. How about the medical safety and can you comment on that? Because things diffuse into your bloodstream and then you have no control over what's happening.
Yeah. So the question was, what is the safety? What are the safety implications of using nano on the body, and how can that really be an advantage if there's some toxicity concerns, right? Yeah, that's an excellent question. And so there have been lots of studies done on on carbon nanotubes and how they go across the skin interface. There have been studies done on particles, nanoparticles, and how they can be inhaled inside the lungs. and perhaps reside there. And so those are unknowns at this point. And so in terms of nano interfacing with the body, that is an area that I mentioned sort of in the broad sense of biocompatibility. Anything that touches the body, whether it's inside or outside, has to be assessed for that point. But there's another opportunity in nano that is perhaps a lower hanging fruit, and that is using nano in the electronic components that go to make the sensor system work. For example, the nanoelectronics for the energy harvesting, or the nano features for the energy harvesting. If you have thermoelectrics that are made out of nano superlattice layers, those will have a higher efficiency of energy harvesting than, for example, the traditional thermoelectrics, but they don't have to touch the skin. Another example would be gas sensors that are made out of nanowires, which will have a much lower power consumption level, and again, they'll be exposed to the air. So you can categorize nano's toxicity in terms of its use, field of use. Yeah.
I have two questions. The first is about the microphone sensors you were discussing. What kind of current developments are there for cases where you do have power, for example, in healthcare facilities to use those type of microphones to monitor things like breath sounds and quantify those?
Yes.
And my other question is, can we learn anything from the relatively long-term battery life of devices such as pacemakers?
Yes, yes, good questions. So the first question is, what is the current status of using microphones in healthcare environments where battery life is not an issue? You can plug in the wall. And that's actually being done. So Bosch and Kyonix, I believe, are companies that are selling microphones that are very low power levels and that are being used exactly for that application. Now, whether or not health sounds are pervasive in the hospital environment, that's another development. But they are available as voice or sound recognition sensors. And your second comment was about the
relatively long-term
battery lifetime. Pacemakers require very low power levels, and so these are in the sub 10 microwatts. So it's very easy to get those devices to work for very long periods of time. In fact, they're even talking about providing pacemakers with energy through wireless means, through RF sources, or even ultrasound. If we can build our sensor systems that work at that low power levels, then we'll be in very good shape. But because we have so many components that require power, it's a little bit of a challenge. But certainly in some of the work going on in our center, we are addressing complete sensor systems that work around 100 microwatts. So not sub 10 like the pacemakers or in that range, but we're getting there. Yes?
What components of the system consume the most power in the system that
Yeah, that's a great question. So in today's devices, and John will talk about this in great detail, but in today's devices, it's the radio that consumes a lot of the power. But as the radios are being lowered in power level, then other components start showing up as energy consumption block. For example, there is some work at TI that shows that if you can reduce the power levels of the radio, now suddenly the analog front end starts taking more of the power level. So what do you do with that? If you have 5 different sensors hooked up to your sensor system, do you need 5 different analog front ends? That's going to, all of those added up together will use a lot of power, so maybe you have to have a flexible approach where a single front end, analog front end can use that. So I think what we want is most of the power to go to the sensors. So if we can lower the power level of every other component on the block, then we can now start putting more and more power towards multiple sensors as long as the system on chip doesn't dominate the power consumption. But it's a changing point.
Computation eventually should diminish because we can use the radio to
we can just transfer everything. Yeah. And that's another interesting scenario where do you process everything on the node or do you transmit to the smartphone and process it there? It's not clear right now.